Yes, good morning, all the students. Let's start our seventh lecture and the last lecture of this module 2. In the previous class, we have discussed on issues in decision tree learning. And the first and most important issue that have to be addressed by the machine learning experts when they are trying to use this decision tree as the model to fit their data is avoiding overfitting the data. Overfitting the data is the model is learning too much from the data, and it is okay with any kind of alternative values to the attribute, so that it can't generalize well, it can't predict well with the unseen data or with the new data points, right? That is called as overfitting of the data. This has to be avoided. It should not be misunderstood that overfitting is a good performance, because overfitting will give good accuracy on the training data but not on test data that we have seen with the help of some graphs, right? So you should understand that overfitting should not be mistaken as good accuracy, right? So this overfitting have to be avoided by various methods like error reduced pruning, in order to reduce the decision tree to less number of nodes, to make it more simpler by removing the nodes that doesn't contribute to the accuracy or performance of the decision tree. And we also have seen another method called as rule post pruning. Rule post pruning method will let the decision tree grow and overfit till the extent possible, and after that, by formulating the rules based on the condition, based on the attribute values, if you remove a precondition, then see if the performance is increasing, you can keep that rule removed, prune that rule off from your decision tree. That entire branch can be removed. If it is contributing well to the decision tree, then it has to be retained, right? These are the two methods: error reduced pruning and rule post pruning. These are the two methods which we have seen to avoid overfitting of the data. There are many such methods, but these two methods are mainly discussed because they are practically much efficient to be used and much easier to be used, right? Now let us proceed with the next issues, simple issues which can be easily understood and how exactly they can be addressed, right? Incorporating continuous values attributes, alternative measures for selecting the attributes, handling training examples with missing attribute values, and handling attributes with differing costs. So in this chapter, another important question is discuss on the issues with decision tree learning and how they can be addressed. Okay, this chapter is very small, hardly it has two important concepts. First concept is how to build a decision tree by considering the measures entropy and information gain. So when some training example set is given to you, you should be able to build the decision tree by taking into consideration the statistical measure called as information gain, which further uses entropy. Okay, that is one important question in this chapter. And the second one is issues in decision tree learning and how to address those issues, right? These are the two topics you have hardly in this chapter, right? So if you focus on these two topics and understand in depth very clearly, you'll be able to answer your second question. Okay, and not second question, third or fourth questions, right? Now, let's proceed with the other issues in this decision tree learning. The next issue coming up is in incorporating continuous valued attributes. How to incorporate continuous valued attributes? See, normally decision tree is meant to work with discrete valued attributes, right? Discrete valued attributes means yes or no. There is a categorization between the label, right? Yes or no, true or false. defaulter or not, genuine transaction or a fraudulent transaction, right? There is a categorization between what has to be predicted, male, female, right? There is a specific categorization for the outcome label. But in continuous valued attributes, can you do that? Say if I'm trying to predict the sale price of a house, or I'm trying to predict the marks acquired, marks obtained by a student, or percentage obtained by a student. They are not discrete valued attributes. Did you understand the difference between discrete valued attributes and continuous valued attributes? If there is clear separation between the values, it is called as discrete valued attributes. If there is clear classification or categorization between the attributes, they are called as discrete valued attributes, right? But in continuous valued attributes, percentage can be any number between 80 to 100, suppose, right? Again between 80 and 81, you have 80.1, 80.2, 80.3, up to 80.9, right? It is continuous. You can't have a clear cutoff between the two values 80 and 81, right? This is called as continuous valued data, right? So in order to make this continuous value data to be incorporated with decision tree learning, what has to be done? Normally decision trees work very well with only discrete value data, but in order to incorporate even continuous valued attributes, what measures have to be taken? How to address these issues? Let us see. Our initial definition of ID3 is restricted to attributes that take on a discrete set of values. Yes, we know that. Now, the target attribute whose value is predicted by the learned tree must be discrete value. That is a restriction, right, on decision tree. And the attributes tested in the decision nodes of the tree must also be discrete value. Not only the target attributes, even the attribute values, even the attribute categories, even the attribute labels, that also have to be discrete valued. See, if you take temperature, high or low, if you take sky, sunny or cloudy, right? There is discrete values in the attributes. There are discrete values in the attributes, right? But assume a condition, assume a scenario, if temperature is given in the form of numbers, 22.3 degrees Celsius or 25.7 degrees Celsius. In that case, how to categorize? In that case, how to make the decision tree learn? Because decision tree very comfortably learns with discrete data. But if continuous data is given, how does it learn? That we are going to understand. This second restriction can easily be removed so that continuous valued decision attributes can be incorporated into the learned tree. How can we do that? By just giving lesser than a specific value, branch onto left hand side. If greater than a specific value, branch onto the right hand side, right? But how to consider that, how to decide on that value, greater than or lesser than? How is it possible? Again, information gain will come to our rescue. It will save us. It will help us to find out which will be the best comparison that gives us the best information gain in order to split the training examples. Okay, so this can be accomplished by dynamically defining new discrete valued attributes that partition the continuous attribute value into a discrete set of interval. So we are trying to give interval. If x is greater than this and lesser than this, let it fall on this branch. If x is greater than this and lesser than this particular range, let it fall on the right hand side branch. That is how we need to build a decision tree with continuous valued attributes. Now let me give an example so that it will be very clear for you. For an attribute A that is continuous valued, the algorithm can dynamically create a new Boolean attribute A. How we are trying to create a attribute, new Boolean attribute. Now that is true if A is lesser than C and false otherwise. Say A is lesser than 10,000 annual income. Yes, get all those training examples. No, get all those other set of training examples. Right? That is how you need to give the attribute values. Say if you are studying the data about a customer. Okay, his income values are given. Income values are continuous valued attributes. Continuous valued attributes means it can be 5,000, 6,000, 7,000, and it can also be 12,000, 13,000, and so on, right? It is like a numerical value. Now, how to develop a branch in the decision tree with respect to this particular node? How to do that? By giving an interval or by giving a relational operator there. If income is lesser than 10,000, for all training examples that is true, put it on one specific branch on the decision tree. That makes one classification. And if information is greater than 10,000, it branches to other side of the decision tree, right? That will give you a different classification. What we are doing here, if it is lesser than 10,000, true for all that, yes or true, all those records will be classified onto one side, and income greater than 10,000, all those training examples will be classified onto the other side. Okay, this is how we are building an interval. Lesser than 10,000 fall on one branch, greater than 10,000 fall on another branch. Means we are trying to convert continuous valued attribute into a discrete valued attribute, which will be answered as yes or no to a condition given as the attribute name. Very simple, right? Simple transformation of the data so that the decision tree will be comfortable with the continuous valued attribute converted into discrete valued attribute, right? Now, the question is how to select the best value for the threshold C. Okay, income level in this customer data case, income level I have taken as 10,000. Less than 10,000, do this, greater than 10,000. Okay, this classification. Now, I can also take 15,000, lesser than 15,000 annual income, greater than 15,000 annual monthly income, or lesser than 50,000 monthly income, greater than 50,000 monthly income. Where to stop this? Which one to select as the threshold? Which one to select as this condition, 50,000 or 10,000 or 20,000? How should I decide on that? The question is how to select the best value for this threshold C. That is most important, right? Let us see an example and understand it. Suppose we wish to include the continuous valued attribute temperature in describing the training example days in the learning task play tennis. Now let us take the same example, play tennis, which has 14 days data. And in that we have values and attribute values as outlook, sky, wind, humidity, 4 attributes we have. Now, and temperature also, 5 attributes. Now, temperature is actually recorded as high, moderate, low. But let us take it as given in this case. Temperature as 40 degrees, 48 degrees, 60 degrees, 72 degrees, 80 degrees, and 90 degrees. Right? In this case, how can we decide on an interval so that we can change this continuous valued attribute into a discrete valued attribute, so that you can give as temperature less than 60, all those falls into one branch, temperature greater than 60, all those fall into another branch. But my question is whether it should be 40 or 48 or 60 or 72 or 80 or 90, because all these values are given here, right? I should not be partial to select a particular temperature. What is the criteria for me to select that threshold C? See where the outcome variable is changing, outcome label is changing. Take an average of those two temperatures and find the information gain with that being taken as the split point. I'm repeating again. In this case, temperature and play tennis, focus your attention on this table, on this part of the slide. Temperature 40, play tennis label is no. Temperature 48, play tennis label is no. When the temperature is 60, play tennis label is yes. There is a change in the outcome label. Take these two values. Find out the average of those two values. It will be around 54, right? Now, take temperature greater than 54 and less than 54 as your threshold value. And see the classification. How best is the classification done? Find out its information gain. You know how to find the information gain, right? Entropy of all the training examples minus the entropy of training examples at that particular attribute value. That will give you the information gain. You have the formula in your previous slides. You can refer to it after the class if you have a doubt. Now I can't repeat that entire thing once again here. It will delay the progress of our class. Okay, so assuming that you all understood what is information gain, I'm telling you to calculate the information gain at the average point. What is the average point here? 54. Now take temperature less than 54, temperature greater than 54, some classification will be done. Find out the information gain with that temperature threshold taken as 54. Okay, next. What else can we take? Again, after this 60, outcome label hasn't changed for 72 and outcome label hasn't changed for 80, but outcome label has changed for 90. So take this combination 80, 90 because it led to a change in the outcome label. Now find out the average will be 85, right? Now take the information gain when the split point is taken as temperature 85, temperature less than 85, make the classification. Temperature greater than 85, make the classification of the training examples. Now find out the information gain with that threshold 85. Now which threshold is giving good information gain, 54 or 85? Take that as your threshold. Very simple, right? Again, let me explain once again here with the help of this slide. What threshold based Boolean attribute should be defined based on temperature? A threshold C, 54 or 85. That is the threshold we are testing. A threshold C that produces the greatest information gain have to be selected. How to come up with this approach? Let us see. Sort the examples according to the continuous attribute A. Initially, these are given in sorted order, but if not, they are given in sorted order. First, sort them. Sort the examples according to the continuous attribute A. Right. Now, identify the adjacent examples that differ in their target classification. These are differing in their target classification. No has become S. And this has differed in the target classification. S has become no. Right? Take that set and find out the average of each. Identify adjacent examples that differ in their target classification and generate a set of candidate thresholds midway. Midway means average. Midway between the corresponding values of A. So you'll get a threshold C equal to 54 here and you'll get a threshold C equal to 85 here. That is nothing but the average of 48, 60, it is 54 and 80, 90, it is 85. So you have taken the threshold. Now make the classification with respect to temperature less than 54, greater than 54. And classification with respect to temperature less than 85, greater than 85. Where is the classification best? Where is the information gain more? That is your selection of the threshold, right? Now, obviously we can see here, because this is a simple example, we can see here, where is the information gain more? This has come to the last. There are not many training examples left, but here with C equal to 54, you can get a better classification than when C equal to 85, right? That is what we are doing here. In this example, there are two candidate thresholds. For this, corresponding to the values of temperature at which the value of plate tennis changes, that is 48 plus 60 by 2, that will give you 54, and 80 plus 90 by 2, that will give you 85 with this. Understood clearly? Any doubt with this, students? Now, the information gain can then be computed for each of the candidate attributes: temperature greater than 54 and temperature greater than 85. What will happen here? Temperature greater than 54, yes, all will be classified onto one branch. No, all will be classified onto another branch. Right. Again, take temperature greater than 85, all will be classified into one branch, and temperature less than 85, all will be classified into another branch. Training examples, they'll be classified onto either branches. Now calculate the information gain by taking this classified examples and this classified number of examples. Where is the information gain high? That will be your split point. So the information gain, we can, after calculating the information gain, we can find that temperature greater than 54 split point will have the highest information gain. So select that as the split point. Other one can be left out. This is how we can convert continuous valued attributes given under temperature by taking the information gain with the split point and make it comfortable for the decision tree to learn from it. Right? So this interval, finding out this interval is important. Finding out that threshold is important. Got it? Now, what are the other measures for selecting the attributes? Let us see. Alternative measures for selecting the attributes. There is a natural bias in the information gain measure that favors attributes with many values over those with few values, right? So when you are calculating the information gain, what is the bias there? Where you have large number of training examples that are obtained onto the leaf nodes. You remember the decision tree in the previous class? When a classification is done, some examples say D1, D2, D3 are brought onto this leaf node, and D5, D7, D9, D10, D12 are brought onto this particular leaf node. Now, the bias of this information gain measure is that it favors attributes with many values over those with few values. Okay, so where there is perfect classification, say 8 negative examples are there and 2 positive examples are there. In that case, we say this attribute is giving good information gain. That bias we have. Now, consider the attribute date. Let us consider a new attribute introduced into this example data set, that is date, which has a very large number of possible values, right? If you take in March, the data set is collected for whether the tennis is played or not, given the weather conditions and the date. Understand carefully. Date has 30 possible values. And on a given date, tennis is played, yes or no? There is only one possibility, right? And given the date, immediately it can perfectly classify whether the tennis is played or not. There is no ambiguity like outlook depends on sky, depends on wind speed, depends on humidity. There is no such dependency with date. On a specific date, the tennis is played, yes means yes. On a specific date, tennis is played, no. No means no itself. There is no further ambiguity in that. So you will get only one level tree, but many branches. As much as 30 branches are possible in March. 31 branches are possible in March. 30 branches are possible in April. 31 branches are possible in May. What is happening here? For every possible date, you are getting a perfect classification. But does it generalize well to the unseen data? That is our question. That is our criteria to select an attribute. Because date is perfectly classifying the outcome, because date is perfectly classifying the training example based on the outcome variable, we can't say it as a good predictor. Why? Let's see. If we were to add this attribute to the data in play tennis, it would have the highest information gain of any other attribute. It can have highest information gain than any other attribute. Why? Because it makes perfect classification, right? But why is it not a good predictor? But this decision tree would fare very poor on subsequent examples because it is not a useful predictor despite the fact that it perfectly separates the training data. Though date perfectly separates the training data, there are 30 dates given, 30 branches will be built and you have perfect classification. But it is not a good predictor. Why? It can't generalize well. Now a new date is given. Where is the branch available for that in the decision tree? There is no branch. How can it predict on that particular attribute then? Say it learnt everything on March date. Now a new data is given with April date. It wonders what to predict because there is no branch to proceed with that prediction. Means the generalization of your decision tree is being reduced because of being okay with every possible date, because of being okay with every possible alternative. So what is wrong with this date attribute? It has so many possible values that it is bound to separate the training examples into very small subsets, right? If it is on this date, very small number of subsets. On this date, very small number of subsets because hardly one or two matches may be played on a particular date, right? Then only those examples will be classified with that particular date as the attribute value. What will happen now? Because very less number, because of this it will have a very high information gain relative to the training examples. Yes, information gain is high because classification is perfect despite being a very poor predictor of the target function over unseen instances. Now when some unseen instance is given, when some unseen example is given where the date is different, there is no branch in the decision tree to proceed with the prediction. It will stand wondering what has to be predicted, whether yes or no, because it doesn't know the new date. That is the disadvantage of completely relying on information gain, right? One way to avoid this difficulty is to select decision attributes based on some measure other than information gain. So we can't solely rely, we can't completely rely on information gain itself because of this kind of traps that may be posed or that may be challenged by this kind of attributes called as date. So what is the alternative? One alternative measure that has been used successfully is the gain ratio. Instead of information gain, we call it as now gain ratio, which further filters out the attributes such as date, what we have discussed. Okay, the gain ratio measures penalizes attributes such as date, what we have considered, by incorporating a term called split information. Okay, now what is the split information? It is sensitive to how broadly and uniformly the attribute splits the data. So it considers how broadly and uniformly the attribute splits the data. If the attribute is splitted narrowly means if the training examples are very less on the leaf nodes. On this date, only two matches are played. So only those two matches are classified. On the other date, only 3 matches are paid, only 3 matches are classified. What is happening here? The broadness of the training examples that are brought onto the leaf node is very less. It is splitting too much, right? So that split information, let us calculate as S and A. S means the split information with an attribute A, as this measure is somewhat same like entropy itself. Okay, so the number of subsets that are split by this attribute value by the total number of training examples log the number of attributes split with this threshold, the number of subsets by the total number of training examples. This will give you the split information. Now, if this split information is high, means uncertainty is high, information gain will come down by this formula. Okay, now let us first see where S1 through SC, S1 through SC are the C subsets of examples resulting from partitioning S by the C valued attribute A. Okay, C valued attribute means, say A is dates in March. How many values will C have? 31 values. Now, when there are 31 values, this SI will increase so much, right? When this SI increases so much, entropy also will increase. When entropy increases, split information will increase. Now, how this plays an important role in understanding the information gain? The gain ratio measure is defined in terms of the earlier gain measure as well as the split information as follows. Gain of S of A, you know how to calculate, right? What is the information gain of the training example set by taking attribute A as the split point? You know how to calculate this in your previous topic, information gain of S of A. But this has to be now divided by the split information also. Means if more are the subsets that are being split onto the leaf nodes, if there are more number of branches, if denominator increases, what will happen? Numerator reduces. Numerator reduces means gain ratio reduces. Means the information gain with that particular attribute reduces. That itself will tell us that is not a good selection of attribute. Why? Because date is giving lots of branches. Though it is not giving more levels, it is giving lots of branches. Now, if you select date as the split point, your tree will start expanding like anything. Your tree will become complex. In order to avoid that, we have formulated this, the scientists have formulated this gain ratio. That gain ratio is gain, information gain with the training examples when A is taken as the split point divided by the split information when A is taken as the split point. Now that will reduce the information gain if the split information is more. Means if the subsets divided by this threshold C are more, in that case this gain ratio will be less. If the gain ratio is less, do not select that as the split point. Simple decision, right? Notice that the split information term discourages. Discourages means as this increases, split information increases, the numerator reduces, means the information gain reduces. The selection of attributes with any uniformly distributed values. Notice that the split information term discourages the selection of attributes with many uniformly distributed values. Date is giving uniformly distributed values. Split information of date will be higher. That will reduce the information gain with date. So you can easily decide that date is not a good split point, though it is giving perfect classification. Do not be misled by only information gain. Take the gain ratio. It will help you take a decision that whether that date is a good predictor or not, whether the date is a good attribute for classification or not. Very easy now, right? Not only information gain, now we are considering gain ratio also. Now, hereafter it is very easy. Other two issues, right? Let us proceed without any confusions. Handling training examples with missing attribute values. If there are missing attribute values, how to handle that scenario? In certain cases, the available data may be missing values for some attributes. Say, blood test result is available only for a subset of patients. For other set of patients, blood test results are not available. They haven't done the blood test, so they can't report those results. In that case, that attribute will be empty for them. In such cases, it is common to estimate the missing attribute value based on other examples for which this attribute has a known value. Normally what they do, they either take the mean of before and the after attribute and put it in that particular attribute value, or they take mode of the attribute values. Mode means frequently repeated value. Most of the patient's blood test result is this much. So put that for this missing value also. Those are such different kind. There are different kind of such approaches in order to put values into those missing attribute values. But let us take it more formally. Rather than giving median, rather than giving average, or rather than giving most frequent value, let us do it more formally in order to get good information gain. Consider the situation in which gain of S of A is to be calculated at a node N, say humidity. In the decision tree, to evaluate whether the attribute A, that is humidity, A is humidity, node N is the nth node, say first node or second node or third node, like that. Calculated at node N in the decision tree to evaluate whether the attribute A, that is humidity, is the best attribute to test at this decision node. Okay, now we are trying to find out whether humidity is the good split point in order to get pure classification. Now suppose that X is the set of all the attributes for a training example, and C of X, the outcome label, is one of the training examples in S, right? And that the value A of X is unknown. Now, for this training example set, one attribute value is unknown. Let us take the example. Okay. Now, what is our plan 1? Plan A, plan B, they'll tell, right? What is plan A? Assign the missing attribute value, the value that is most common among training examples at node N. Okay, that particular node, there are some classifications available, right? Say by checking Outlook as the split point, classification is done. Now after classification is done, 4 training examples have come onto this leaf node. Now on this leaf node, how many of the training examples are having one value with respect to this attribute A? Say more number of examples, I mean. Okay, say 3 examples are having value 10 and 1 example is having value 5. Then select 10 as the blood test result for that missing value. Okay, that is what is mentioned here. Assign the missing attribute value. What value? The value that is most common among training examples at that particular node N. So in those 6 training examples, 5 examples are having blood test result as 10 and 1 example is having blood test result as 8. In that case, for the missing attribute, give the value as 10 itself. That is one plan. What is the other alternative plan? Assign it the most common value among examples at node N that have the classification C of X. This is actually the other way what they are telling. In those 6 training examples that are classified, 5 of them have S and 1 has no as the outcome label. Now among these S values, what is the most repeated value for blood test result? Take that value, put it in the missing attribute value for the blood test. That is another plan. Now, in some learning tasks, the instance attributes may have associated cost. How to handle attributes with those differing costs? Cost means what? Some attribute is very important for the prediction. Some attribute is not that important for the prediction. Or say, when you're taking a medical test for a patient, some medical tests will be very costly and patients may not may not be comfortable to take those tests. Only some tests they'll take up. So for those tests, the values will be 0, missing. For the other tests, the values can be taken. Right? In this case, some are having values under those attributes, some are not having values under the attributes. Means, what is the other way of understanding it is, some tests are having good weightage to predict, but some tests are not having good weightage to predict. In some learning tasks, the instance attributes may have associated cost with them. For example, in learning to classify medical diseases, we might describe patients in terms of attributes such as temperature, biopsy result, pulse, and blood test results. Now, most of the patients' temperature and pulse will be available, and even blood test results also will be available because measuring them is of lesser cost or easy. Okay, but biopsy result, most of the patients doesn't, they are not comfortable to take up that test because it is uncomfortable. Also, it is little costly. In that cases, these 3 attributes will serve as good predictors where most of the values will be missing under this attribute. So temperature, pulse and blood test results will be given higher cost. Biopsy result will be given lower cost in terms of their contribution to predicting the outcome variable. Got it? These attributes vary significantly in their cost. How? With respect to what? Both in terms of monetary cost. Biopsy result is very costly. Biopsy test is very costly. So they may not take up the test. Those attribute values will be empty for most of the patients. So there is no use in using that particular attribute in predicting the outcome variable. But it has to be included. In that case, give it lesser weight because most of the patients doesn't want to take up that one. But temperature, pulse and blood test results are very easy to be taken up. Give them more weight. Means they contribute more in predicting the outcome variable, whether the patient has a particular disease or not, like that, right? And cost to patient comfort also, as I said. Sometimes cost, monetary cost means medical test cost or comfort to the patient. Sometimes the patient may not be comfortable to take up the test. In that cases, give such kind of attribute lesser cost, lesser weightage in predicting the outcome variable. In such tasks, we would prefer decision trees that use low cost attributes. What are the low cost attributes here? Temperature, pulse and blood test result. We would prefer decision trees that use low cost attributes where possible, relying on high cost attributes only when needed to produce reliable classifications. So only when there is ambiguity in the classification with the low cost attributes, only then go for the high cost attributes. Until then, build the decision tree with the low cost attributes only, because lots of data will be available with low cost attributes. Low cost attributes means you're giving them higher weight in prediction. Do not get confused between high weight and low cost. Low cost means it costs low to the patient. So all such data is highly available. Means they are contributing more in predicting the outcome variable. So give more weight to low cost variables. That is what I'm trying to tell you. Okay. So this temperature is low cost variable, but high weight variable in predicting the outcome variable, outcome label. Pulse is low cost variable, but give it higher weight because it contributes more in predicting the outcome variable. That is how you need to understand, right? In such tasks, we would prefer decision trees that use low-cost attributes where possible, relying on high-cost attributes only when needed to produce reliable classification. So always build decision trees on low-cost attributes and assign them more weight in predicting the outcome variable rather than high-cost attributes like biopsy result. Okay, so how this can be further understood? ID3 can be modified to take into account attribute costs by introducing a cost term into the attribute selection measure. Let us introduce a cost term so that ID3 algorithm machine can understand better how to go forward with this differing costs. For example, we might divide the gain by the cost of the attribute so that lower cost attributes would be preferred. Very easy this is, do not get confused. We might divide the gain, information gain, by low cost attributes. Low cost attributes means information gain will be high. High cost attributes means denominator increases means information gain will be low. So that will give us information about the low cost attributes and the high cost attributes information gain. Right? Now, while such cost-sensitive measures do not guarantee finding an optimal cost-sensitive decision tree, they do bias the search in favor of low-cost attributes. This is one disadvantage. When we take this low-cost or cost-sensitive decision trees, they may not guarantee us optimal decision trees. Why? Because we are having a bias towards low-cost attributes. We are trying to eliminate the usage of high cost attributes because they don't provide good information gain. So our tree will be obviously biased towards this low cost attributes only. Okay, and another example, if you take a robot perception task in which the robot must learn to classify different objects according to how they can be grasped by the robot's manipulator. Say there is a robot, it is trying to classify the objects. Before classifying, it has to learn how an object looks like. So it has some sensors which will scan the objects and it will create attributes for the objects, say edges or flat surfaces or round surfaces. It will try to scan them and create some attributes. Now, how much time taken to scan each attribute may be the cost. Consider like that. Okay, now scanning the edges is taking too much time. Scanning the round surfaces is taking lesser time. Then the robot will tend to use round surfaces to recognize the objects rather than edges. It is biased towards objects having round surfaces because it is taking less time to scan those features rather than scanning the edges. In that case, how the information gain can be changed? Gain square of, rather than taking normal information gain, they are taking square of the information gain and dividing it by the cost of that particular attribute, right? So the cost increases means as the cost increases, the information gain reduces. As the time taken to scan a particular edge increases, information gain with that reduces for the robot in learning. So it obviously tends to take round surfaces because the cost of that attribute is less, means time taken to scan round surfaces is less. When the denominator is less, information gain will increase. Obviously, it will go towards round surfaced objects only to learn better than compared to edges, learning with edges of the objects. Right? This is another example, that's all. Okay, so what we are trying to understand here is wherever the cost attribute cost is less, there the attribute may contribute more to the prediction. That is why decision tree tends to build the tree with respect to those attributes only, rather than taking high cost attributes. Right? In textbook, it is too lengthy. So those students who want to learn more better on this concept, you can go to the textbook and refer. But in the slides, I have given sufficient information for minimal reference to present as answer in your exams. Okay, so by this we completed our second module. Let's just paraphrase quickly what topics we have covered. We have seen introduction to the decision tree algorithm and the decision tree representation and appropriate problems for decision tree learning and the basic decision tree algorithm ID3 and hypothesis-based search in decision tree learning. We have seen that by using ID3 algorithms performance with measures, information gain and entropy, and inductive bias in decision tree learning, that is preferring shorter trees for larger trees, and also using a statistical measure called as information gain. These are the two assumptions made in decision tree learning and issues in decision tree learning like overfitting and say varying costs or having continuous valued attributes. How to deal with all those issues we have covered. What is the time? Okay, we have only 5 minutes. Yeah. Can you quickly answer what is overfitting? Students? What is overfitting? Learning too much or learning too less?
Learning too much.
Yes, learning too much from the training examples is overfitting. That doesn't make it generalizable to the unseen data. Underfitting means learning very less. That also can't generalize very well with the unseen data. Okay, so what is generalizability of of a machine learning model? Predicting correctly with unseen data. That is called as its generalizability. Now, what is the inductive bias of decision tree learning? What are the two assumptions we make in decision tree learning, students? Quickly. Preferring shorter trees when compared to larger trees or complex trees, and using information gain in order to build such short trees. Right? What is entropy? Uncertainty in the classification is called as entropy. What is information gain? How well the classification can be done. That measure is called as information gain. How is E related to IG? I want you to answer this, students. How is entropy related to information gain? Directly proportional or inversely proportional? Students? Entropy is directly
Inversely
proportional
proportional.
to. Very good. Inversely proportional. Uncertainty in the classification increases, information gain reduces. Uncertainty in the classification reduces, information gain increases. What is the reason to perform pruning of decision trees? One crisp answer. What is the reason to perform pruning of decision trees? Why do you prune the decision trees? To avoid. Please answer. To avoid. To avoid what? To avoid what you cut the trees? Overfitting.
Overfitting, ma'am.
Very good. After me answered, be quick. What are the two methods of pruning? At least this you answer, please. What are the two methods of pruning? Error reduced pruning and other one?
Rule was pruning.
Very good. Rule post pruning. Error reduced pruning, where the error has to be reduced when some pruning happens, or rule post pruning, when some rule is removed, performance have to be increased. If the performance is not increased, retain the rule, do not prune it. Okay, that is the criteria in order to prune the trees which are resulting in overfitting. Right, this is how we conclude our second module. We are taking too much time in concluding in completing the syllabus. So you have to be fast in your understanding, students. Right, go through first and second chapters quickly once. and see if you have any doubts, you can ask me before going to the third module tomorrow. Okay, we'll end the class here and meet in the next class.